Here from organizing team, who is there?
Ma'am Asha here.
Okay. So I think people will join slowly.
Okay.
Speaker join.
Uh,
Yashaswini.
Yashaswini ma'am, I can't see her name here.
Uh, Send me the link. I will.
Okay. Okay, ma'am.
Okay, I have. I will give you. Somebody B Kishore. Kindly switch off your camera. B Kishore. Asha ma'am.
Yes, ma'am.
Some B Kishore is there. For
Okay,
that
ma'am.
person, tell the switch off the camera.
Hello, Sir Kishore, sir. Hello. Please switch off your camera, sir. Hello, Kishore, sir.
Yes, yes, Ashwini.
Hi, ma'am.
Yeah, yes.
Good afternoon, ma'am. How are you?
Okay, so we will start now.
Yes, ma'am. Yes.
Can I start, ma'am?
Yes, yes, you can start.
Okay.
Uh,
Good afternoon, one and all. It gives me immense pleasure to extend a warm welcome to all distinguished participants of today's faculty development program. Our gathering today is enriched by the presence of an eminent scholar and educator, Dr. P.R. Yashaswini, Assistant Professor in the Department of Electronics and Communication Engineering at Malnad College of Engineering, Hassan. Dr. Yashaswini's impressive academic journey serves as a beacon of inspiration to all of us. With a formidable background encompassing both research and teaching, she brings a wealth of knowledge and experience to our esteemed program. Her 5 years of dedicated research and 3 years of nurturing young minds in the classroom exemplify her commitment to academic excellence and pedagogical innovation. Having earned her Bachelor of Engineering degree from Government Engineering College Hassan, followed by a Master of Technology in VLSI Design and Embedded Systems from Rajiv Institute of Technology Hassan, Dr. Yashaswini has demonstrated a relentless pursuit of knowledge and proficiency in her field. Her crowning achievement, a PhD on design and performance analysis of photonic sensors for various applications from Malnad College of Engineering, underscores her expertise in photonics, optical sensors, and optical devices. Dr. Yashaswini's scholarly contributions extend beyond the confines of academia. Her numerous research papers published in esteemed peer-reviewed journals stand as a testament to her rigorous inquiry and intellectual prowess. Furthermore, her authored book, Fundamentals of Semiconductors, serves as a valuable resource for students and scholars alike, demonstrating her ability to distill complex concepts into accessible knowledge. In addition to her academic achievement, Dr. Yashaswini's proficiency in various software platforms, including MATLAB, Cadence, Xilinx, ANIS Numerical, MEEP, Opti FDD, Mr. Kishore, please mute yourself. Kishore sir. Kishore sir, please mute yourself.
అనుపమ ఐటీ సిఎస్ఐ అంటే వాళ్ళ సిఎస్ఐలో చూపిస్తుంది
అనుపమ ఫామ్ 26 ఇయర్స్ లేదు ఇప్పుడు
Rita ma'am,
ఉండదు తీసేసాను తర్వాత
Yeah, yeah.
you can mute ma'am. You have
No, I don't have control.
అయిపోయిందా
I don't have control.
okay.
As a guest, I join.
Just a minute.
సిఎస్ఐ ఇంకెవరు ఉన్నారు
అనుపమ అయిపోయింది కదా కీర్తన ఇంకా ప్రవళిక కూడా ఉంది హారిక కూడా ఉంది ఫామ్ సిస్టమ్ లేదు హారిక ప్రవళిక లోహిత కీర్తన
Asha ma'am, who is that person we have to remove? Name?
ఇప్పుడు ఇచ్చారా
ఇంతకుముందు
Kishore, ma'am.
Kishore.
Be Kishore.
Kishore.
He is muted now.
He muted, ma'am. He muted.
No, we are doing. Kishore, we have muted, no? Who else is there? Who else is there? We can mute them.
That's it. Only
Huh?
one.
Only one? Okay. Okay, Asha ma'am, continue.
Asha, unmute yourself and continue. Asha ma'am, unmute yourself and continue.
Yes, ma'am. Yes, ma'am.
Yeah.
As we embark on this journey of professional development and academic enrichment, let us seize the opportunity to learn from Dr. Yashaswini's expertise, insight, and passion for advancing the frontiers of knowledge. Her presence promises to elevate our demonstrating, inspire our teaching practices, and empower us to make meaningful contribution to our respective fields. Please join me in extending a heartfelt welcome to Dr. P.R. Yashaswini. Over to you, ma'am.
Thank you, ma'am. Thank you, Asha ma'am, for the wonderful introduction. And first of all, I would like to thank Preeta ma'am and the whole Oxford College of Engineering for this wonderful opportunity. Thank you so much, ma'am. And shall I share this screen, ma'am? Hello? Am I audible?
Yeah. Yes, ma'am, you're audible. Please share your screen.
Okay.
Yashaswini, your PPT,
Yes, ma'am.
you are not here, Yashaswini?
Ma'am, I'm sharing it.
Hello, Yashaswini.
Is it not?
Yashaswini?
Hello?
Hello? Hello?
Hello?
Yeah, it's just, you are there.
Yes, ma'am.
You have to,
Am I not audible, ma'am?
you have to share your slide.
Yeah, I was sharing it.
Okay.
But after once I started sharing, I think I was not audible.
Just again try. Asha,
Now I am audible, no, right?
yeah, you are audible.
Yes, ma'am.
Asha, you coordinate with her.
Yeah, yes, ma'am.
Now am I audible, ma'am?
Yes, you are audible.
Slide presenter. Asha? Preeta ma'am, shall I continue?
Yes, yes, you continue.
Yeah, yeah.
Yeah.
Yeah. Good afternoon, everyone. So today's talk will be on the design of photonic crystal-based pressure sensor. And as we have already seen in the entire series about the photonics and the quantum, so almost everybody will be knowing the basics of photonics, but still I'll just touch upon the basics, and we will be seeing the what are the photonic crystal configurations and what is the defect engineering, and also we will see different types of pressure sensors in the different ranges. So basically, in this slide, I have considered three ranges. That is, in one in gigapascal, one in megapascal range, and one in kilopascal range. So that we'll be seeing all the different pressure ranges, and we'll be seeing how to do it in different software tools. So basically, so what is photonics? So photonics is derived from the word photon and electronics, and we all know that it's the science and application of light. In the photonic application, we use photons in the similar way that we use electrons in the electronic applications. So coming to why we need photonics is the future, and we know that light travels faster than electricity, and there's a big need to make things faster, less energy consumption, smaller, and cost efficient. So replacing electrons with photons does all of this. And also we know that the optical way, the data be carried in a higher, and the data rate transmission and reception will also be very fast. So that is the main aspect that we are going towards photonics, and photonics will definitely be the future. So coming to the different applications of photonics, it is very difficult to say in which application we can't use photonics. So that is the range of applications that we can use photonics in. So I have just mentioned few of these here, like in lasers, we can touch upon photovoltaics, LEDs, integrated photonics, and one among the all these applications are photonic sensors. So we can use it for filters also, and there are several applications. But today we are considering the photonic sensor application. So coming to that, in the bios and how it uh, we consider pressure sensor, photonic crystal based pressure sensor.
Yashaswini ma'am,
Basically,
your voice is breaking.
now, ma'am.
Now it's a bit better.
Reports connected wire. One second.
Yeah.
Is it fine now, ma'am?
Yeah, it's fine. It's fine now. Thank you.
So, photonic crystals, they are the periodic arrangement of dielectrics in certain directions. So, depending upon along how many axes do you have periodic arrangement of dielectrics, our photonic crystal can be of the type one-dimensional, two-dimensional, and three-dimensional. So, in the figure also you can see that the green color and say it is a dielectric A, and blue color is dielectric B, and it will be repeatedly placed in a certain fashion. So depending upon how many axes we have those periodic arrangement of dielectrics, so the photonic crystal will be of one-dimensional, two-dimensional, and three-dimensional. So next is the crystal configuration. So there are two crystal configurations as we know. The one is rods in air and the other one is holes in slab configuration. So the rod-like blocks are created on the air in order to form the waveguide. So that will be rods in air configuration. And if we take a silicon or if we take a slab and if we take a what we can say base or a slab, and if we create holes in that, so that will be holes in slab configuration photonic crystal. So these are the two basic crystal configuration types. Next, coming to defect engineering. So in order to form the photonic crystal and in order to make it to work as a sensor, the most important part is defect engineering. So basically why we use defect engineering is to manipulate those photons or to control those photons in proper directions. So in order to, we can say that in order to form the waveguides, in order to make certain movements in the in whichever way we want. If we want the light to move in that fashion, so then defect engineering is the most important thing. So in that defect engineering, we can do the defects by using line defect or point defect. So creating a defect, it is nothing but we can either remove that hole or rod, or we can replace that particular hole or rod with different size, shape, or the dielectric constant. So that is called as defect, making a defect. If one hole or rod is made into a defect, so that is called as point defect. And if the entire line is removed or entire line is replaced, so then it is called as line defect. So these are all the basics. So now we'll get into different design of the photonic crystal based pressure sensors in different ranges. So basically, as I have already mentioned, so here I have considered three different ranges, one in the megapascal range, another one is gigapascal range, and another one is kilopascal range. So that from smaller to higher pressures also we can pressure sensor. So it is so first application will be in the megapascal range, that is 0 to 6 megapascal range, and the second application will be for the gigapascal, that is 0 to 3 gigapascal range, and the third application will be for the kilopascal range, that is 5 to 20 kilopascal range. So all these modeling and simulation, it is done using FDTD and the FEM tools. So first application, it is to sense the pressure from 0 to 6 megapascal range. So for that, what are all the design steps for in order to create a photonic crystal based pressure sensor? What are all the design steps? We'll see that first. So the same design steps holds good for others as well. So the first application, it is done using the FDTD tool called as ME. So here in this, first we have to define the design parameters. So what are all the design parameters? Then we have to create a mechanical model of the same thing, whatever the design or the structure that we create in ME, the same structure should be created or modeled using ANSYS tool. Then there, after creating the structure, we have to apply the pressure at the center of the diaphragm, and we have to calculate the stress, strain, and the deformation values. So why we have to calculate these values is, so we can't give the pressure, we can't apply the pressure directly in the MEP software. So what we'll do is we'll model the same thing in the ANSYS, and we'll calculate, we'll apply the pressure there. We will get the stress, strain, and deformation values, and then by that values we will calculate the RI values, and then we'll give the RI value into MEP. In the MEP structure, we'll give it. So that by using RI values in the MEP code, we can tabulate the transmission graphs, and we can observe and tabulate the resonance wavelength shift also, and we can calculate the design parameters like quality factor, sensitivity, and so on. So this is the MEP structure that I have considered. So this is a hexagonal ring resonator with a bus waveguide above and below it. So the same structure is extended to 2 rings and the 3 rings also for the same application. So these are all the design parameters. So this is the MEP structure, and once we generate it in the MEP structure, as I already told, the same thing is modeled in the ANSYS platform. So similarly, this is the structure in the ANSYS platform for 1 ring, 2 rings, and 3 rings. So for this, what we will do, we'll apply the pressure at the center. We will then tabulate the stress, strain, and the deformation values. And by using those values, we will calculate the RI value of the pressure that is applied, and then we will give it into me. So here, so this is the, we can see that the pressure is applied at the center in the figure 9. So next, these are all the stress and strain values that is obtained for the pressure from actually from 0 to 6 megapascal. Here I have mentioned as 6.3 micron because we have started from that value, but basically it is varied from 0 to 6 megapascal. So after this, so this is for the 2 rings and 3 rings. So by using these formulas, so we'll calculate the, by using stress values here, we'll calculate the RI values. So you can see here. So these are the RI values for all the directions, X, Y, and Z directions. So here we'll consider the X direction RI values for the MEP structure. So by taking these RI values and providing it to the holes that is created in the MEP structure. So it means that, see, if like for here we can see that for the pressure range of 1 megapascal, the RI value is 1.0089, right? So the same RI value, when we give it into the MEP structure, I mean the holes of the MEP structure. So the meaning is that we have applied 1 megapascal in the MEP structure for that structure. So, so these are the RI values for the 2 rings and 3 rings. So after applying the RI values, after simulation, we will be getting the resonant wavelength shift for the 1 ring. So here we can see that there is a shift in the resonant wavelength. So basically the photonic crystal sensors, it works on the principle that when there is a change in the RI, that is when there is a change in refractive index, there will be a change in the output response. That is, the wavelength will be shifting. The wavelength will be shifting. So that wavelength shift, based on that wavelength shift, we can say that what is the pressure that is being applied. So this is for the 2 rings and 3 rings. So similarly, these are the overall tabulated results. That is the wavelength shift and the amplitude for the different pressure ranges for 1 ring, 2 rings, and 3 rings. So after calculating all those, so the basic major important thing parameters are sensitivity and the quality factor. So the sensitivity is calculated by the equation 4, and the quality factor is calculated by using equation 5. So in this application, the sensitivity obtained was 450 nanometer per RIU, and the quality factor obtained was around 12,245. So this structure, it is done using the MEP software. So yeah, and here I have compared it with the another paper also, whatever the paper that I had referred. So with that, if we compare it, so the quality factor, it is improved in many folds actually. In the first paper, it was 1966, but in this paper, the quality factor, it is increased to 12,000. So yeah, for pressure range for 0 to 6 megapascal, we can say that our structure works better compared to the paper one structure. So next is the same for the same application. I have modified a little bit of the structure and did the same structure using ANSYS numerical software. So this is the structure, and these are the design parameters. So here we can say that by doing analysis by changing the radius of holes, we can see that there is a increase in intensity value, and also the quality factor is also being increased by varying the radius of holes to from 130 to 130. I think I had varied it from 120 to 160 actually, in like 120, 121, 122, and so on. But here I have just mentioned it from 133 to 144. by varying the radius of the holes, we can see that the quality factor is improved at 138 nanometer of the radius of holes, and after it is like after it is increased to 139, the quality factor started dropping. So that from this we can do the optimization, like by changing the radius of holes, we can improve the quality factor. And here from previous quality factor, it was 12,200. But here the quality factor, it is around 15,083. So
Hello.
here we can see the.
Ma'am, I have one question here.
Hello.
Hello, I have one question here.
Yeah.
Yeah, as we know, in ANSYS tool, we can apply pressure directly. Is there are
Yeah.
any options or methods of applying a pressure in numerical software as well?
Yeah, actually, yeah. In as you told, in ANSYS we can directly apply the pressure, but in
Yeah.
numericals, we have to do the same thing as I have explained. Uh, as we do the application of pressure in ANSYS, and we will take the RI values, right?
Yeah.
RI values, and we'll give it to me. In a similar way, we have to do the same thing here also. We have to design and apply the pressure there in ANSYS, and we'll take the stress values, and we'll calculate the RI value using those formulas that I had shown here.
Mm-hmm.
Just a minute. Yeah, this one. By using this, we have to calculate the RI values, and then we have to apply it into the ANSYS numerical software. So similar thing. So as we do it in me, the same thing we have to do it in the ANSYS numericals also. Because in numericals also, you don't have the option of applying pressure directly. So we have to convert that applied pressure into RI, and then we have to give it into the numericals.
Okay. Okay. Thank you, ma'am.
Yeah. So this is the graph of intensity with respect to radius of the holes, so that we can see clearly that as we vary the radius of the holes, so we can optimize the quality factor very well. So these are the output spectra, or the transmission spectra of the proposed sensors. So here we can see the resonant wavelength also. It is very narrow. And the next application is for a pressure sensor in the gigapascal range. So for the in that also in that application, I have designed for two different structures. So one is ring resonator structure, and the another one is triangular structure. So basically here what we see is in that gigapascal range, which structure works best for which pressure range. So that is the basic thing. And these are all the design parameters that I have considered. Here we have used ORSOF tool for the simulation. So this will be the output spectra. Here we can see the output spectra, and the same thing is it is compared with the referred paper also. So that is the reason that I have put the referred paper. So coming to the results. So here you can see that the quality factor for different pressure range from 0 to 3 gigapascals. So here we can see that in the ring resonator structure, so the quality factor, it is high from the pressure range of 2 to 3 gigapascal. So it is high in the pressure range of 2 to 3 gigapascal range. And coming to the triangular resonator, we can see in the results. So the quality factor, it is high from 0 to 2 gigapascal range. So that by this analysis, we can come to the conclusion that if we are working with a pressure sensor, which has to sense the pressure from 0 to 2 gigapascal range, we can directly opt for triangular resonator. And if the pressure range is from 2 to 3 gigapascal, then we can directly opt for ring resonator structure. So the next application, it is the pressure sensor for is the that we have sense it will be in the kilopascal, that is very low pressure range. So the application that is considered here is barotrauma. Barotrauma is when there is a stress on the eardrum because of the change in air pressure. So then it will cause a disease called as barotrauma. We can't say it as a disease, it's a condition called as barotrauma because the eardrum may rupture. So when it is an excessive pressure greater than 20 kilopascal, it will rupture the eardrum. So this pressure sensor, it will be very useful for the divers basically. So like scuba divers or skydivers. So they'll they are very prone for this barotrauma because there will be a very abrupt change in the air pressure and the water pressure. So it will be very useful for the divers. So here I have considered two structures. One is ring resonator and the another one is semicircular resonators. So the Q factor for the ring resonator was 3877 and for the semicircular structure it was 4933. So in this application, if we want to sense the pressure for 20 kilopascal, I mean 20 kilopascal and below, so it is opt that we go for semicircular structure. So here, this design, it is done using the JCM suit. So this is the proposed sensor design. One is ring and another one is semicircular. So these are all the design parameters. And these are similarly as we have done in all the previous applications. We have varied the pressure, we have taken the stress and strain values. Then again, the difference here is, so there was a wavelength shift there, but here we can see in the waveform that there's an amplitude shift. So based on the amplitude shift, we can diagnose the pressure that is being applied. So these are the tabular columns for ring and the semicircular structure. So we can see that the quality factor for semicircular will be it is much higher. I mean, little bit higher than the ring structure. Coming to the conclusion. So basically, there are. I mean, here we have. Taken a survey like for different pressure ranges, what are all the structures that is opt for with different applications, and we have find out the quality factor, and by doing the analysis of changing the radius of the holes, how we can improve the quality factor. Thank you. If there are any questions. Hello.
Any question from participant?
Hello, ma'am. Since you have worked in many software, which will provide the better results?
Yeah, it is basically you have to, I mean, it is not like which will bet it will provide, I mean, I can't say this particular software will provide you the best results. So it is like for different applications you can use different softwares, and as far as I know, we have used in different softwares. But coming to the quality factor, I feel like the numericals and RSoft. So both will give you a little clear clarity of transmission spectrum. And to the MIP, it is a coding software. So I mean, you have to write the code and then you have to do the things. And coming to numericals, you have to write the scripts. So there are little changes. I mean, we can't say this is the best in the software.
And here one more thing I will add in this connection. If you want to do the fabrication, then always better to go for the licensed version of software like RSoft or Lumerical. These two are the licensed version software. So PDK will be easy for this. It is same line of action as VLSI. So the license version Like recently, Mentor Graphic, which is for VLSI software, in their library they have added this numerical software. Very recently they have added, so that manufacturing or fabrication will be easier in the same lab. But for practice, MEP and all is good, just for the knowledge sake. Opti is there, many free software is there. Opti FTDD is a free software. Morning hands-on session was there, na? That is a free software. MEP also free software. But RSoft and numerical we have to purchase. Any other question?
Hello.
Yes, yes.
Hello, ma'am. You have shown us the analysis part and how the G factor is being improved. So what are all the changes that can be done, optimize the structure properly?
Yeah, I had explained you, ma'am. Like to improve the quality factor, there are certain things that can be done. Like one is in the analysis part I had shown you. So you can vary the by actually the basic things are the radius of the holes, the lattice constant, and the coupling gap. In the ring resonator that we had considered, the coupling gap should be, and also the width of the wavelet. So these are all the things. So one analysis part actually I had shown you in that presentation. We had a table of radius that is increasing radius, and once the radius it hit 138 nanometer, the quality factor was high. And as you do the analysis, if it is increased to 139 nanometer, the quality factor started dropping off. So by keeping the lattice constant as constant, you can vary the radius and see how the quality factor will be varied. And also by doing that also it can be improved. And also by keeping the radius constant, you can do the same analysis by varying the lattice constant. So that can also be done. And you can vary the what is that coupling gap, and you can see how it will be properly optimized. So these are all the various things that you can do.
Okay, ma'am. Thank you.
Hello, ma'am. May I audible?
Yeah, yes, sir.
Hello, ma'am. I am myself Dr. Benji Pathak from Allahabad, UCR College. I want to know for getting the best result, which wave guide we have for which wave guide we have to use first, such as a circular wave guide or technical. Which wave guide we have to
Which
use
wave
for,
guide?
such as a circular
So
wave
to
guide or linear wave guide or triangular wave guide, hexagonal wave guide. So the number of hexagonal as a one-way hexagonal, two-way hexagonal. So the parameter of performance as increase or they get more best result.
so sir, actually again we can't say which is the best waveguide for directly, like oh, I can't just say that ring resonator is the best type of waveguide, so that for all applications it will be the best. So again, it will come to which application that you are considering, and by doing the literature survey, so you'll be knowing that. So which structure will be better in which application. So for like if we come to pressure sensing application, we can say that hexagonal ring resonator will be best in that section. And if you go for like what you can say biosensing application, it will vary. If you go for temperature sensing application, it will vary. So if you want to start the simulation, and if you are in a confusion that which structure to go to, so I'll recommend to do a literature survey on the application that you are considering, so that you will be knowing the exact structure that you can start.
Okay, thank you. Good afternoon, Peter ma'am. Good afternoon, Peter ma'am. Hello, ma'am.
Yes, yes. Good afternoon.
Uh, Ma'am, what is the cost of our soft and numerical software, ma'am?
Yeah, RSoft is a licensed version software. For that, where we have procured, in that system only we can use, because they have given the dongle like a pen drive. Without using that, we can't do. So like we have purchased, so we are having that dongle. So whoever is doing in RSoft, they are coming. Even Yashaswini came here and she has done here. So RSoft, wherever it will be there, they have to come there and they can use. It's a licensed version software. Free software is there, FTTD, that is a free software. And second free software is the MEP. So anybody want, they can do in MEP also and Opti also. But RSoft is a, we have to purchase because it is a licensed version
Okay,
from
thank you.
Synopsys company.
Okay.
So any more question? In chat box, Yashaswini, can you see in chat box? Sometimes people will write in chat box.
No, ma'am. Today, no questions in chat box.
Okay. No problem. Her presentation was quite clear. So those who are in this background, they have understood, I think, completely. So nice it is. So before ending the session, wind up the session in formal way, which Asha will do. We will tell the participant who are present to on the camera. So we will have a group photo and then we can bind the session. So those, it is, if it is possible, please on the camera. Okay. Okay. So Asha madam, can you take the
Yes, ma'am.
photograph?
Yes, ma'am.
Okay. Because previous speaker gave this idea. Previous speaker request was there. She want the photograph with all the participants. It was the request from the previous speaker, Vishalakshi from Singapore. So she told me, we want like that. So I gave this idea. I got this idea that in few we should have the photograph. So very nice.
It's a
2, 3
beautiful
photograph
idea.
you can take, Asha madam.
Yes, ma'am. But many haven't turned on the camera.
Oh, okay, okay. No issue.
Yeah.
How many he has done? You just take.
Yes,
Okay.
ma'am.
One thing I will tell actually, now talk is over. Yashaswini was not in a position to give the talk. She is giving the talk from the hospital, and in this condition, some problem is there, and then also she agreed to give. Really, I am very thankful, Yashaswini. Thankful to you.
I'm very thankful to you, ma'am.
I pray to God that your
Whatever,
father get recover soon. Yeah.
thank you so
She
much.
has proved where there is a will, there is a way. She
Yes.
has done it.
Actually, we have learned these gestures from Preeta ma'am. Actually, she's not only been a support in the matter of whatever photonics group and everything. It's a different matter, ma'am. But how women should take the life. So we have seen and learned from her. Thank you so much, ma'am. Thank you for the opportunity.
We all women are fighter. I was very tense because last moment she told, even she has not informed me also. Last moment she wrote, but somehow she managed to take this session. Thank you. Thanks for that.
Thank you. Thank you. Thank you so much, ma'am.
Okay.
Thank you, everyone.
Okay, Aruna madam is from Dayanand Sagar. She is also there. Mhm. Okay. So Asha madam, take the photograph. Many has turned on the camera.
Yes, ma'am.
Okay, thanks. Thanks to all of you who joined. Thank you.
Thank you.
So formal way, Asha, now you can wind up the session.
Sure, ma'am. Yeah, ma'am, sure. Okay. On behalf of Oxford College of Engineering, I would like to extend my deep sense of gratitude to Dr. Yashaswini ma'am for accepting our request and sharing her knowledge in the field of photonics crystal and design of pressure sensors. Thank you, ma'am, for sharing the design process in such a great detailed manner, applications of the same, and clearing so many doubts as well. And thank you all the participants for your enthusiasm and active participation. Thank you all.
Thank you. Thank you.
Thank you.
Asha madam, feedback link you can post now.
Yes, ma'am. I shared it in the group, ma'am. I have shared the feedback in WhatsApp group. Please give your valuable feedback. Thank you.
Okay, some of the this one is asking the session was very informative. Please provide the recording.
Yeah,
Sharath
we will
Sarathi.
share the link soon for a morning session as well. We'll provide you the YouTube link.
Okay.
Yeah.
Okay. Thank you. Thanks a lot.
Thank you all. Thank you, ma'am.